Many people are aware global climate change is important for ecological interactions as well as for human health. As for some of the ecological factors that are affected by global climate change, we have to look no further than the intensity and frequency of forest fires, flood risks, the retreat of glaciers, as well as the likelihood of drought. These are all things that are impacted by global climate change. Of course, there are also several implications for biodiversity and ecological interactions between species. Moths are incredibly common and play important roles in ecosystems worldwide. They are also very diverse, numbering over 12,000 species in North America alone. But despite their ubiquity, there is much to be learned about the details of the interactions they play in ecosystems and how these interactions will be affected by global climate change. Because they are ectotherms, moths are very affected by the temperature external to their bodies. When the weather is warmer, moths typically develop faster, and when it is colder, they typically develop slower. There have been several studies where people have monitored the flight times and emergence times of moths and butterflies across a 20-year time span. What they have found is that in warmer years, moths fly earlier, and in cooler years, moths tend to fly later in the year, a result that pretty much makes sense given our understanding of basic insect physiology. Frequently, these warm temperatures are associated with more recent years because of global climate change. These studies are really informative, but it takes 20 or 30 years to conduct one of them. One counterintuitive finding that comes from these studies is that many species of moths are not actually that sensitive to climate change. That is, they are not strongly affected by these small 1 to 2 degree changes in temperature. But a really counterintuitive result is that some species actually emerge later when they are warmer. Because some species respond one way and others respond in other ways, it is of interest to try to understand why species respond in these different ways, and which species will respond in these different ways. This is of interest because ecological interactions might uniquely be affected because of these differential responses of species. What students and I have been doing to get around this issue of having to wait 30 years to observe climate change is that we have studied moths along a spatial gradient instead of a temporal gradient. And we've been utilizing a technique first popularized by Henry Cowles, which is known as space for time substitution. So instead of waiting for 30 years, you can just go over a certain spatial distance and observe similar changes in temperatures. In our case, this space for time substitution occurs along an urban to rural gradient. That's because temperatures are typically warmer in an urban environment, like a big city, and cooler in a more rural area. This local climate change, due to city effects, can mimic the kind of differences that we see over the next 50 to maybe even 100 years in global climate change. But all you have to do is travel 30 kilometers or so to see these differences in temperatures. Before we continue, it's important to understand what urban heat islands are. Basically, there are areas around a city that are hotter because the city is absorbing solar radiation all day throughout the day, then re-releasing that radiation throughout the night. This creates a dome of hotter air surrounding cities in comparison to more rural areas. These are common in cities above about 200,000 people and are especially influential in megacities like Baltimore, New York, Atlanta, etc. But before we could determine the effect of Birmingham's urban heat island on moth phenologies, we had to determine whether Birmingham actually had an urban heat island first. So we set out temperature probes at several different locations, and these probes recorded temperatures once an hour for several months. What we found is that there were slight but reliable differences in maximum temperatures, or the daytime high temperatures, between the rural, intermediate, and urban sites. The biggest differences that we saw, though, were in the minimum temperatures, or the nighttime lows. This is where urban heat islands are especially influential. In urban areas, it does not cool down as much at night because the city is re-radiating all that heat that it has absorbed throughout the day. As a side note, there are sociological implications of this phenomenon all over the world. Think of the fact that many who live in big cities are poor, and that they are paying for more air conditioning than people who live in less urbanized areas with less pavement. The next question was, does that heat island have the anticipated effect on moth phenology? Other studies have looked at whether urban heat islands, like the one in Phoenix, Arizona, and in several other places, have influenced the flowering time of several plant species. In this figure, you can see that for most species of plants in the study, flowering time was earlier inside the city than for that same species of plant outside the city, although there is one interesting exception. What we wanted to know is whether these heat islands impact moth phenologies as well.